Okay, let's begin. So, we started talking about integrals last time. We're going to pick up on the same stuff. Let's see what did I do last time. Continue with 5.2. Some things to recall. One very important fundamental theorem of calculus, which basically says part one. It basically says the integral from a to b f of x dx is equal to big F of b minus f of a. Here, big F of x equals the antiderivative of x. It's a very important theorem. I.e., if you differentiate f of x, the answer will be small f of x. That's what it means to be the antiderivative of something. For example, position is the antiderivative of velocity, because if you take the derivative of position, you get velocity. All right, so that's one interpretation. And basically, we can find the area under a curve by subtracting different values of its antiderivative, which is very interesting. It's something that's kind of surprising that ended up happening. So that's one thing that you have to remember. This is how we compute what's called a definite integral. These are integrals with numbers on it. We also have the so-called indefinite integral. Right, so it's just the integral of f of x dx. And the answer would be f of x plus c. This is called the general antiderivative. Or indefinite integral. It is the function that gives the area under f of x on some interval. There's a plus c, so it's not unique. You can have many antiderivatives for a particular function. What else did we talk about? 3. We talked about the basic rules of integration. Basically, we obtain these by reversing the derivative, because we know that this guy is the antiderivative of that guy. So one was the power rule. The antiderivative of x to the n is, what was that?
Plus 1.
X to the n plus 1
Over n plus 1.
over n plus 1 plus c. So you kind of reverse what you did with the power rule for derivatives. Right? This works for n not equal minus 1, and this is called the power rule for integrals. It's basically a shortcut to find the area under a curve that looks like x to the n. We also had another one. In the case where n is equal to minus 1, x to the minus 1 is actually 1 over x. And for that one, we know the answer is what?
So reduce 1n.
So we come back to ln. Right? Because if I take the derivative of ln, I get 1 over x. Notice here that we have absolute values. So your x can be positive or negative. Another one we have is e to the x dx. We know that is e to the x plus c, because the derivative of e to the x is e to the x. we'll see later today where this formula comes from, but we can generalize this formula a little bit because it's convenient to do so. We can talk about integral of e to the kx dx, where k is a constant. It's just actually 1 over the constant e to the kx. Let's see. K not equals 0 is k constant. So any of these rules you can figure out just by reversing the derivative rules. I don't think we use this one often in this class, but you could also reverse the rule for a to the x, which is just going to be a to the x divided by ln a. But these three are very important. We're definitely going to be using these all the time. So those gave us some shortcuts. Also note that we have some properties. These I didn't mention last time, even though for some of the exams we kind of used it. One property is, again, just like with derivatives, we have a constant factor rule. Meaning if I take the antiderivative of a constant times a function, it is the same as taking the constant times the antiderivative function. So constants I can factor out. Tons of ways you can see that. Remember that this guy is really a Riemann sum. This is saying every term of the sum has a constant. You can factor it out of everything. There are tons of ways to see that, but that is one important rule. That constants we don't have to worry about. We can always sort of factor them out and worry about applying a basic rule to a more basic function. We also have a sum and product rule. So if I have f of x plus or minus g of x dx, I can integrate one at a time. So that's f of x dx plus or minus the integral of g of x dx. And we'll be using that. Again, because it's a Riemann sum, I can split a sum into two parts, so I can split an integral into two parts. There's also a curious fact of I can flip the limits on an integral by actually just taking the negative of that integral. Why is that? Tons of ways you can see it. Probably the easiest way is the fundamental theorem of calculus. I know that this guy here is equal to big F of B minus big F of A, which I can think of as the negative of big F of A minus big F of B, which is just the negative of, this would be the top number, that would be the bottom number. So we have that property, and you'll see where that comes in handy later as well. One other property that will come in handy in chapter 6 is the fact that we can split definite integrals up into pieces. So for example, another property, if I have the integral from a to b of f of x dx, I can think of that as a to c of f of x dx plus c to b of f of x dx. I can split up an integral in between them. An illustration, this is not a proof, but it's just to illustrate what I mean. Remember, if this is your f of x, then the integral from a to b of f of x dx is just equal to the area of that guy. But the thing is, that area I can actually split it in two parts. I can think of it as the area from a to c, and then add the area from c to b. Right, so the integral from a up to c of f of x dx gives me that area, and then I add that to the integral from c up to b of f of x dx, which gives me that area, and then I add them together to get the total area. Right, so There are times when I'd like to split up my integral and just know that we can do that. So these properties are very important. You'll see them applied in chapter 6. This one we're going to apply before chapter 6. In fact, this one we're going to start applying now. Let's get started with some examples. We did similar ones at the end of last class, but we're going to start to get more and more complicated with these. Not super complicated, but more complicated. I think we even did some of it.
Number 4, where did the C come from?
It's a convenient number that you can put in. Like in chapter 6, you'll see where we do it. It actually doesn't matter what the C is. Any number on the real line and it'll work. And again, you can even prove that using the fundamental theorem of calculus. So many things you can prove from this. But you'll see where something like this might come in handy. When we talk about errors between curves, sometimes splitting up the integrals is going to be necessary. Okay, let's start with this one. What do we do?
X to the 2 plus 1 over x.
Right, so you just get x
3.
cubed over 3 plus c, because you did that over rule x to the 2 plus 1 over 2 plus 1 plus c. So you'll get that as the answer. This one?
So the 4
So the 4 over 4 plus a constant. Notice that if you differentiate this, you'll get that. What we did, I just applied the power rule, x to the 3 plus 1 over 3 plus 1.
Turn it to a half. X to the half. And then we do the same. X to the half plus 1 over half plus 1.
What's that?
So 3 halves. the property of addition?
And what would you get?
X over X plus 1 over X.
Then what?
Over X.
That would have absolute value of x. Very important that you put the absolute value. Notice that in general, just like how with derivatives, when you have a division, there's like a whole rule that you have to be worried about, like there's a quotient rule. For integrals, it's kind of the same thing applies. You can't actually take the integral of the top and bottom and divide it, or an integral of a product and divide it. The rules actually don't work, right? So what I had to do when I see something like this, try to simplify it to look like a basic rule, and then I apply the rules from there. If you just did the integral of the top and then divide by the integral of the bottom, you'd actually be wrong. What about this?
It'll be the same as 2 over 3x over 3 over 2.
Okay. And what about this guy? What would I get? So here I rewrite this as x to the 1/2, and now you did what here? And then what? Do the power rule here, get x to the 3/2 times 2/3. Here do the power rule, so you add 1 to the power, you get what? -1 divided by -1 is the same as multiplied by -1. Let's see. What about this one?
Take out the 3.
Take out the 3 from where?
From the first one. It's constant.
Yeah, but it's going to affect this one. I can't take out the 0.
It stays the same, and you deal with the second part?
How do I deal with the second part?
You write it 7x to the -3.
Right, now you find the antiderivative of each piece. So now you look at the antiderivative of this, you notice that there's a constant in front, but remember we have the constant factor rule, so I don't care. That constant just stays, and then I find the antiderivative of this guy, just like with derivatives. Antiderivative of e to the x, e to the x, plus c, right, which we'll do at the end. Antiderivative of this. Again, constant factor rule, leave the constant alone. Then anti-differentiate that. What do we get? It's a -2 divided by -2. Let's see. So at the end of the day, this is 3e to the x plus, because minus divided by minus, 7 over 2 x to the -2. So constant factors, you can ignore them kind of like with derivatives. Some more examples. do we do here? Yeah, this is just a half e to the x. Right, so how do I deal with that?
It's the same.
So it's the same. You leave the half alone. Antiderivative of e to the x is itself. So you're just left with e to the x over 2. What about this guy? So the third over 3. Right. But now remember, this is a definite integral. I have numbers on the integral sign. What does that mean? What do I do?
You have to substitute.
I'm going to have to plug them in. Now, remember notationally, we mentioned this last time, you write a line like this. You don't put a plus c, you write a straight line. Put the 1 here, you put the 3 here. It's just convention to write it like that. And then what do you do with those?
You plug them in.
You first plug in the 3. You plug in the top number first, right? You're going to plug it in for all your x's. So you have e cubed over 2 plus 3 cubed over 3. Then what?
So,
Then what?
so
You can think of this guy as big F of 3. So what are you supposed to be doing? You're supposed to subtract something. That's the fundamental theorem of calculus. What are you supposed to subtract?
the other
Same thing,
fraction,
but with
plug in 1.
Plug in the bottom number second. So that's e to the 1 over 2 plus 1 cubed over 3. Because it's a subtraction, you need parentheses. That guy here is your big F of 1. Right? So the integral from a to b is big F of b minus big F of a, where big F represents the antiderivative, the function you get after applying one of the basic rules. Right? And so at this point, you can simplify e cubed over 2 minus e over 2. And here you'll have 3 cubed over 3, which is just 9, minus 1 over 3. Right? So, or you can even think of that a different way. You can think of this as 27 over 3, minus 1 over 3, you get 26 over 3. So, that would be the answer. Any questions on this? This one.
Ln of 3. 3x to the minus 1.
Why would you do that? So Barrett says 3x to the minus 1, and then what?
The constant goes both sides.
What?
To multiply by the constant.
Multiply what by the number?
It's gonna be 1 over 1 if you do the power of
No.
What about if you proceed with the bar 4 and 1? Like this.
This is 3 times 1 over x. Does that help?
Oh yeah.
3 ln of x.
Between 1 and 4. And so what do we get here? 3 ln of 4 minus 3 ln of 1. Can you simplify ln of 4? Can you simplify ln of 1? 0. Log of 1 is 0. So the answer is just 3 ln of 4. Okay, are we kind of getting the idea? Okay. That's too easy. Let's make it harder.
Come on.
Let's move on to 5.4. Talk about something called integration by substitution. Because I'm sure you guys are getting bored with these. Let's take it up a notch. This is the first non-elementary integration technique, where it's not just applying a basic rule straight off the bat. It's pretty much the only integration technique you're going to use. So it's nice for it to apply something like this. So one thing you want to know what this is, it's actually a technique to integrate composite functions. Right? Basically, this is the integral analog to the chain rule. Right? So if you have a function inside of a function, you're kind of going to want to think of integration by substitution to do it, if a basic rule won't work. Use when a basic rule does not apply. The idea here is to make a substitution to transform a complicated function into a simpler function. So you can integrate it. And complicated basically means not a basic rule. Simple in this context means looks like a basic rule. Here's the strategy, which might sound confusing, but when we start to apply it, you'll get used to it, right? So basically, this is going to be something that we're going to use to integrate more complicated functions. Right? So if something doesn't look like a basic rule, like when we had these guys, we could sort of finesse them to look like basic rules, but sometimes you actually can't do that, and we end up with integration by substitution. So here's going to be the strategy. It's conventional to use the variable u to do a substitution. So you're faced with a random integral. A basic rule doesn't work, right? So basically, in 205, the only other option is integration by substitution. So you kind of know if a basic rule doesn't work, this is what you're going to do. You're going to use u to substitute an expression in your integrand according to two criteria. These are very important that they are fulfilled. One, it makes the function simpler. i.e., looks like a basic rule. Right? So you're going to try to swap something out for the variable u that allows the function to look like a basic rule. That's the first thing. Second criteria is the derivative of the expression that you substitute. Must be a factor somewhere else in the integral. Remember, it's okay if we're off by a constant factor because I can always factor constants off. So, but if there's a constant factor that's different, it doesn't actually matter. I can always factor it out and get rid of it. So these are the stipulations. That's the strategy. Once you have that, once you've made your substitutions correctly, you will swap out. First of all, you will find what's called du. I'll show you what that means. And swap out dx. And make substitutions. You'll end up with an integral you can apply a basic rule to. Integrate then what we call back substitute. That's your strategy. Let me give you an example. Start with that one. Nice example. Relatively an easy one. So the first thing you'll notice here is this doesn't really look like any basic rule that we have. There's a product, and then there's this radical with something complicated underneath it, right? It doesn't look like x to the n. It doesn't look like 1 over x. It doesn't look like e to the x, right? Looks like something else entirely, right? Now, once you have something like that that doesn't actually fit on top of a basic rule, and on top of that, I can't actually simplify this to a basic rule because I can't distribute radicals across sums or anything like that, right? So this is kind of an ugly function, right? Doesn't fit a basic rule. So once we realize it doesn't fit a basic rule, what we're going to try to do is integration by substitution. So I will use u to substitute an expression in this function, right? According to 2 criteria. My goal is make it look simpler. The first goal. My second goal is whatever I substitute, I must be able to find its derivative somewhere else in the function, right? So the first thing I'm going to look at, I'm going to say, what makes this complicated? Right?
Radical?
The radical. And not just the radical. I mean, if it was this, if it were this, it actually wouldn't be so bad, right? I could just write that as x to the 1/2, and then rewrite this as x to the 3/2, and then do the power root, right? It's not just the radical that makes it complicated. It's the thing under the radical that makes it complicated, right? So it's not just the fact that there's a radical, because I can write a radical as a power at any given time, but the fact that there's a sum under the radical, that's what makes it complicated. So now I start to think, well, maybe I can just substitute that. Let u be the thing under the radical. So now I'm going to take a sum under the radical. I'm going to turn it into a single variable. Hopefully so I can do it this kind of trick. Right? So that's the first thing. That will actually make the function a lot simpler, right? Because I could just write that as u to the 1/2 power and do the power rule.
So by plugging you took up the radical?
No, I didn't take out the radical. I am making what's called a substitution. So I'm going to replace this guy with the u, right?
Okay.
So the first thing I do is I put my u to make something that simplifies this expression. Now there's a second thing that I have to be concerned about. When I differentiate this expression, I must be able to find this derivative somewhere else in the function. So then I go and okay, the derivative of u with respect to x will be, what's the derivative of this? 2x. See that 2x? I need to be able to find that expression somewhere else in the function, right? If the 2 is not there, it doesn't matter because we can factor constants out and it's not a big deal, right? But the idea is here, I can have my du is 2x dx. So, having that is very convenient because that allows me to swap everything out. So let me kind of show you how we'll swap it. Kind of two ways. So let me rewrite this. So notice that in my substitution, I'm making this guy u, right? Now by making that guy u, I end up with this guy here. My 2x dx, which is, I can see here, 2x dx. This guy here, that would be swapped out with what? D. So now if I can rewrite this integral, what can I write? Well, I have the radical of this thing, which is u. So I just have radical of u. And everything else, I can replace with just du. Now I look at that, and what do you see? It's a basic rule, right? It's the power rule. This is just the integral of u to the 1/2 du. Right? So now I just do the rule on that. U to the square root of 2 times 2/3 plus c. And then I do what's called back substituting. So u wasn't in my original problem, so I'm going to have to back substitute this u, replace it with x squared plus 1. And I have 2/3, replace my u with x squared plus 1, to the 3/2 plus c. This is what's called back substituting. And that will actually be the answer. Complicated. Let's do another example. You're all looking at me like fish in a fishbowl. Okay. Which is normal, so don't be alarmed. That's actually completely normal. The first time I saw substitution, I was like, what? What the hell just happened? What kind of sorcery is this? Okay, let's do another one. See, look at that guy. So technically I could simplify this to look like a basic rule if I want to expand something 20 times and get 21 terms and expand it into the power rule. I do not feel like doing that though, because you know, we only will have like 3 minutes on a single one of these problems. So one thing I realized here, it doesn't look like a basic rule. It doesn't look like x to the n. It doesn't look like 1 over x. It doesn't look like e to the x. There is no basic rule that applies here, right? It's something more complicated. So the first thing I'm going to think is, what makes it complicated? Why is this a bad thing? Because this guy, the 5x4 plus plus 7 is raised to the 20th power. This inside here is bad. If that was a single variable, like just x to the 20, it wouldn't be any problem, right? I'll just multiply it, add the powers, right? This guy makes it complicated, right? So what would I do here? Substitute. Let u be that guy, the complicated guy. And now I'm just going to differentiate. My du would be 20x cubed x. Right, because I do du dx, you just multiply by the x. You usually skip that. Okay. So now what?
This is just
You
the
can
inside
do
part.
20x cubed.
I differentiate.
Oh.
Derivative of 5x to the 4th is 20x cubed. Derivative of x is 7 is 0. So I have that. Now remember that I want to start swapping things out. But there's a problem though, right? Not insurmountable, but there's a problem nonetheless. Here I have 20x cubes.
You don't
Here I
follow
only
that.
have 3. So the constants don't really match up. How can I fix that? Because here constants don't match up. We have a couple of ways of dealing with this. Okay. So let's do one way of dealing with this. One thing is, in my experience in tutoring, it seems to be the preferred method by students. Solve for dx and plug it in. Which is basically going to be it. I guess the simplicity of that, just a lot of people like. So let's see what it would look like here. Right. So I see that the constants don't match up. What I'm going to do, just solve for dx. If I solve this equation for dx, what do I get? How would I solve for dx?
du over 20x cubed.
Right, I would get du divided by 20x cubed. Right? And now I'm just going to go back to that integral. I'm going to start swapping things in. Right, so you see this integral here, 3x cubed times 5x to the 4th plus 7 to the 20. I'm going to start swapping things out, right? This 3x cubed, I didn't do anything with it. So leave them alone, right? This guy, though, actually changed to u, right? So I'm going to swap that guy out for u. But now I solve for the dx, which means this dx, what can I write now? I can write du over 20x cubed. And what you're going to realize now, these things start canceling. Right? The x cubed here is going to cancel that x cubed there. And now there are no x's anymore, like magic. Right? This is kind of why you need the function part of the derivative to appear somewhere else in the function, so you can do this kind of cancellation. Now, still looks a bit complicated, but not to worry, because we know that constant numbers we can factor outside. So this thing, I can factor out a 3 over 20. And what will I be left over? Just u to the 20, right? du. Now that, it's a basic rule, that's just power rule. So what I would get is 3 over 20, I'm just going to leave that constant there. Just do the power rule here. U to the 21 over 21. It's C, because it's an indefinite integral. And so now I just have 3 over 20 times 21. My U was this guy. To the 20. And that would be the answer. Another way is to multiply or divide by a convenient constant. To obtain the constant that you want. So let's see how that would work. So you can copy this again. When I was learning it, this is kind of how I did it, but I think students prefer the first way, so after this I'll probably always just do the first way. Right, so you get to here, you're like, nice, I got that x cubed, but the constant is off, right? The thing is, it's a constant, I can multiply or divide by whatever. So I know this is not a 20, so what I can do is I can just divide both sides by 20. Like, okay, so far so good. But I know I need a 3x cubed, so I can just multiply both sides by 3. Right? So I just manipulate this equation to get exactly the expression that I have. Right? Which I can just divide out and multiply by whatever to cancel and get something back. So now what happens, I can switch this guy out. Right? I realize that this guy, the 3x cubed dx, which is here, 3x cubed dx, I can replace it with 3 over 20 du. So I just get 3 over 20 du, and that replaces this guy. And then what am I left over with? Just this guy to the 20th power, but that guy is u. So that's just u to the 20th power, and the integral sign is there. Right? So I end up here again, just like I would have normally. And basically you do repeat the rest of the process. You'll end up with 3 over 20 times 21. What I did here?
Yeah.
Yeah, so here I had a 20, and I wanted a 3. So I just did divide out the 20, right, because I don't want the 20. And because I want a 3, I just multiply both sides by 3. I just multiply and divide by constants to get the constant that I want. And then I can swap it out after that. More examples. Okay, go. What do you think? First thing, doesn't look like a basic rule, right? It seems like I have that 1 over x, but there's this pesky little ln in the bottom, which I didn't have a rule for ln, so that kind of messed it up. Can't really simplify this to make it look like a basic rule, so I'm kind of stuck with substitution. It's the only other thing we know in 205. So, question of the day, what do we substitute? Why?
X
You substitute x ln x?
the whole thing.
Well, what do we want to happen? We want to substitute with something that makes it simpler and we can find its derivative. Someone said x on x. Would that have worked? If I take the derivative of that, what do I get?
1 over x.
No. What's the derivative of x ln x? Got to do derivative. You guys can't forget the simple stuff and start learning new stuff. That's not how it works.
Is it hot?
What will be the derivative of this?
Of x is 1.
1 over.
I know the derivative of x is 1. What's the derivative of this? X ln x.
Is it 1 plus element?
What? It's what?
1 plus element?
Right, because you need the product rule, right? There's a product of functions. Differentiate this, leave that, plus you leave the first one, differentiate the second, so you get 1 plus ln x. Now, is there a 1 plus ln x here?
No.
No, right? So that would be a bad substitution. So that's not what we do. Any other ideas?
The whole thing.
Huh?
Substitute the entire thing. What do we do?
Substitute the entire thing.
Yeah.
Okay, well, what if I substitute the entire thing? What would be the derivative of this? Add up x ln x to the minus 1, which when I differentiate, I would get minus x ln x times to the minus 2, multiply the derivative of the inside, ln x plus 1. That's even worse. So that wouldn't work.
Can you use multiplying or dividing? Can you do x squared? I don't know.
The first person was right. It's ln x. I was like, why? Just, you guys need to be more confident in yourself. Come on. ln x was the right answer. Why? If I take the derivative, what do I get? 1 over x dx. And look here, I have 1 over x dx. Right? The derivative is already there. It's just sitting there. This guy, remember, it's just like 1 over x times 1 over ln x. Right? So I have that 1 over x dx, right? Making ln gives me the 1 over x here. Right? So now what I can do is I can just directly swap things out, right? So this 1 over x dx just becomes du, nothing to do. What do I have left with here? One over u, right? My ln was in the denominator. It's 1 over ln, so it becomes 1 over u because u is ln. Now this looks like a basic rule. What is that? What's the antiderivative of 1 over u? It's just ln of u. Right? That's the rule. Well, what is u? U is ln x. So I get ln of ln x. That's the answer.
Jhevon, I have a question. What happens to du when you
Yeah, because we had that rule. Remember, f of x dx equals just big F of x plus c. Right? This is just a notation. It's kind of like when you have that d dx of x squared, you get 2x. This just means a notation that says your independent variable is x and you're differentiating with respect to that variable. This just means your independent variable is x and you're integrating with respect to that variable. It's a kind of a notational thing. You don't think of something happening to this group. So yeah, once you actually apply an integration rule, you get rid of the d part, you just forget it. Just take the antiderivative of this, and that's your answer. Be confident in your answer. Sometimes what students will do, they'll get this answer and they're like, that looks wrong. They question themselves, and then they go back and change something. You know? Kind of like what happened just now when someone said u equals analyze y. Completely change their answer. Right? If you're in a test and you're second guessing yourself, you can't let yourself talk yourself out of the right answer. You need to know why. Why would you pick ln? And so when I asked the question why, you should have said, oh, well, the derivative would be 1 over x, and I can see it there. Right? You should understand why you're doing something. Right? So that way you don't end up talking yourself out of the right answer, which happens often. What about this one? Equals 1 plus e to the x. So your du would be, what's the derivative of this? E to the x dx, which you have right here.
What does that have to do with, like, when you just circle it
I'm circling this. Remember when we're substituting, the derivative of the thing we substitute must be somewhere else. So I'm just emphasizing that. Oh, I see it there. You have to be able to see that somewhere else in the function, right? So once you substitute something as u, like this guy's my u, its derivative must be somewhere else in the function. I have to be able to see it. If I didn't see it, it's the wrong substitution. So what would this become? Right, I have 1 over this guy, which is my u, and this dx is replaced with du. So I have that. And what's that guy? ln of u, and then I back substitute. This guy.
What is it?
Huh?
How do you find that part? 1 over u.
Because if I have e to the x over 1 plus e to the x dx, this is the same as 1 over 1 plus e to the x times e to the x dx. That's my 1 over u, and that's my d. It's just an algebraic thing. You just know that in fractions you can slide the top off and keep it separate and do that. What I do here? It's the what? Right, so you look at this, that makes it complicated, so hopefully if u equals x cubed plus 1, that would work out. To know that it's going to work out, I have to find its derivative, which is going to be 3x squared dx. Now notice here, I have my x squared dx, I have my x squared dx. The thing is the constants aren't the same. Don't worry about it, solve for the dx. And then swap things out. So here, I didn't do anything with that, that's 2x squared. This guy I replace with u, that's radical u. The dx becomes this, du over 3x squared. My x squares would cancel. My 2/3 I can factor out. 2/3 times the radical of u. Just remember that that's u to the 1/2. It's just the power rule. So I have this 2/3 here. Then from this one, take u to the 3/2 times 2/3. That's 4/9 u to the 3/2. By the way, you should, once you actually get an answer, you should be able to check it. One thing you should note that if you take the derivative of this guy, 4/9 times x cubed plus 1 to the 3/2 plus a constant, the answer will actually be the original. 2x squared times the radical of x cubed plus 1. Right? That should happen, right? So if you did something and you're not really sure if you're doing it right, you need to check your final answer. The derivative of your final answer should be the original function that you had before. Right? If you differentiate this, you'd use the chain rule, you'd get that as the answer. X over 5 plus x squared. This is actually from an old final. And this was fall 2011. 2B. Now, I'll show you a couple ways to do that, so let's leave space. What will you do here? Right, the denominator is what makes it complicated. So I'll set u equals 5 plus x squared. Check the derivative. My du will be 2x dx. I have my x dx here, but the constants are different. Don't worry about it, just to solve for dx. I get du over 2x. Start plugging everyone in. And the 3x I didn't do anything with, I leave that alone. This guy I replaced with u, so put that here. My dx is replaced with du over 2x. My x's would cancel. 3/2 factors out.
So whenever you cancel variables, you take the constant out.
You don't have to, but it's easier to see. Because I want to see that there's a basic rule being applied here.
What about if I don't do it? I was gonna look.
If you can understand that this is still a basic rule, then go for it. But you would memorize this, so I kind of write it to look like that. Right? They're the same. But you know, one is easier to see that the answer here would be what?
Elena.
11. differentiate this using the chain rule, you get that. So that was from an old final, fall 2011. Problem 2D. Notice that here, this clearly doesn't look like a basic rule, so I'm definitely going to do substitution here. This is substitution. Definite integral with substitution. Two ways you can look at this. The first way is, by the way, the recommended way. Ignore the limits until all the way at the end. Back substitute before plugging in the numbers. That's very important. So I'm just going to treat this like a normal substitution integral. For the moment, I'm just going to ignore these limits. So how would I do that one? What would I substitute?
ln x.
So I'll say u is equal to ln x. My du would be 1 over x dx. Notice here I have that 1 over x dx. Okay, so far so good. So what would this guy become? This becomes a radical u. This 2 in the bottom, I can always factor it out, that's no problem. du. Now what I say about ignoring these limits, they just tag along, but you have to remember that the limits go with x, not with u. It's very important that you don't mix those two up. So what you can do to remind yourself is right here, x equals 1 to e. To remind yourself that these numbers should be plugged into x's, not u's. So you have that. And you have here u to the 1/2. And you integrate that, what do you get? So you have 1/2 times 2/3 u to the 3/2 between x equals 1 up to e. This is 1/3 u to the 3/2 x equals 1 up to e. So I kind of just, the limits tag along, but I keep reminding myself they're supposed to be plugged into x's, not u's. So before I plug in these numbers, I'll just back substitute first to get the final answer here. U was ln x. And then I apply the fundamental theorem of calculus here. So I take the e, plug in here first. Minus, take the 1 and plug into here. Ln of e is what?
E.
It's 1. Ln of e is 1. So this just becomes a third. Ln of 1 is 0. So the answer is 1 over 2. So just do everything normal. Tag the limits just tag along. You don't kind of ignore them until the very last second. Just remember that once you're given a problem in X, these numbers go with X's. Which means at this point, if you are here, you could not plug the 1 and the E into this here, because it's not X, it's U. Another way is to change the limits. Which personally I don't see the benefit of at this level. If you're doing Calc 2, Math 202, then something like this would be handy if you're doing another integration technique called trig substitution, which is incredibly annoying. But you could actually change the limits as well. So when you have here 1 up to E radical ln x over 2x dx, when you do u is equal to ln x, your du is equal to 1 over x dx, you could also at the same time change the limits. So if u is equal to ln x, when x equals e, this means your u is ln of e, which is 1. And then when x equals 1, this would mean your u is ln of 1, which is 0. And so when you do this whole substitution and you have 1/2 the radical of u du, you can replace the 1 with 0. And you can replace the e with 1. And so you have a new integral now, that these guys actually are the u variables. Right? I just plug in the x values into this equation, solve for the u values, and I replace the limits. And then now I just forget about this problem altogether, and this is my new problem now. So I have 1/2 times integral from 0 to 1. U to 1/2. This comes 1/2 times 2/3 into 3 over 2. So I plug 1 into here. Let's get 1/3. Minus, plug 0 into here. Pretty much a matter of personal preference if you want to change the limits or not, but I probably wouldn't worry about it. I don't think going through this is worth the extra effort you would need. But you can if you'd like to. Ideas? Your du would be 2x dx. I have 3x dx, so solve for the dx. And start to plug stuff in. So here, just remember that this is x equals 0 to 3. And I'm going to, the 3x stays. This guy is radical u. And my dx is du over 2x. X's cancel. 3 over 2 I can factor out. And what would I have left? The x's cancel, so I just have 1 over radical u. Du. Okay, how do I do that? No, I didn't take the integral yet. I have to integrate that first. How do I integrate that? Huh? Right, I have to rewrite it to look like a basic rule. This is just u to the minus 1/2. And I will use the power rule. So you add 1 to the power, gives you a half. Divide by the new power. Dividing by half is the same as multiplying by 2. Twos cancel. So I have 3u to the 1/2. This goes from 0 to 3. Remember that these numbers were the original numbers. They should be plugged into x's. I can't plug them in here. So the first thing I'm going to do is replace that u with what it was before.
16 plus x squared.
16 plus x squared to the 1/2. 2, 0, and 3. So the first thing I plug into 3. Minus, second I plug in the 0. So that's 16 plus 9 is 25, right? And then take the square root of 25, that's just 5 times 3, that's 15. 16 plus 0 is 0, square root of 16 is 4, so it's 12. So the answer is 3. Try these on your own to make sure that you actually understand and you're not just copying mindlessly. That's basically substitution. You get something that's complicated, you simplify it by doing a substitution. Make sure that what you substitute, one, makes the function look simpler, as in you can transform it to a basic rule, and two, the derivative has to be somewhere else in the function. If there's a constant that's off, you just solve for the dx and swap it out, and factor out the constant. It's not going to be able to do that. And that brings us to 6.1, areas between curves. It's kind of the last thing you need to know to do in 205. I will introduce this and we can do examples at the end of next class. So the goal here is to find the area between two curves. To find the area between So the idea is the following, for example. You have an f of x and a g of x, and you want to find the area between these two curves on the interval AB. find that area. Right. It turns out that there's a relatively simple process for getting this done. First, you kind of remember what it is that the integral gives you. Remember, it gives you the area under the curve. So the thing is here. That's F and that's G. This is A and this is B. So basically you want this area. What you're actually going to do is you're going to think of it in this way. You're going to take the area under F, right? Which, let's just shade it like that. Right? The area under all of F, right? Which we know that that's just the area of this guy. How do you find the area of that guy? Well, it's the integral. The integral from A to B of f of x dx. Right? Then what you're going to do is you're going to find the area under G. Shade it like that. This is the area of this guy. Which again, that's going to be the integral from A to B of G of x dx. How do you think I find the area in between them? Subtract. Notice that one area was this guy. The other area was this guy. And so this, we subtract that. Right? Or in other words, because of our properties rules, I can write this as one big integral, a to b, of f of x minus g of x dx. I can combine the integrals. And this, of course, gives us a formula. Area between two curves is equal to the antiderivative of AB of the top function minus the bottom function. So you take top minus bottom, you take the antiderivative of that, definite integral, and that will actually give you the area between two curves. So that gives you a formula, right, which we'll take advantage of next time. So here's something that happens every now and then. Sometimes your functions switch roles. Let's say you have something that looks like this. That's my f of x. And that's my g of x. And I want to find the area between the two functions on a and b, right? Which means I need to find this area here. Now remember, the formula is this. To find the area between those two functions, I need to take the top function and subtract the bottom function. Right? Now what you'll notice here is that that actually switches on, right? Notice that over here, your top function is the f, right? And your bottom function is the g. But over here, your top function is the g and the bottom function is the f. The top and bottom switches on, right? So to apply this formula, you're actually going to need two integrals. And what would that mean here? the integral from a to b of some function, which at the moment I don't know what it is. What I'm going to have to do is I'm going to have to actually split this area into two parts, right? So I know up to this point, let's call it c, right? The top function is my f, the bottom function is my g. So I'll just go from a up to c of the top function minus the bottom function, f of x minus g of x. Then what I'm going to do is I'm going to add the area for the second part. Plus, what's the area for the second part? Well, now that's from c to b. We start from c, go to b. And I'm going to do the top function minus the bottom function. So now it switches on me. You have g of x minus f of x dx, right? This is actually using that formula we had before. The integral from a to b is the integral from a to c plus the integral from c to b. This is kind of the scenario where that concept takes effect, right? It's when you have to break something into two parts, and that's fine. You just do each part one at a time and add them back together. Started on one example, and we'll do more later. So, for example, you can be asked this problem. Find the area of the region bounded between, and they can give you these two functions. Y equals x squared and y equals x plus 2. Now if you look at that picture, y equals x squared is this. But you're not always required to sketch the graph, but you could be asked to sketch the graph. So the problem might say, sketch the area and compute its value. Right? So what would x plus 2 look like? The y-intercept is 2, has positive slope, so it looks like this, right? You know, it's going through 2. So the area between them is obviously this area here. Now remember what the formula to find the area between two curves is. And you take the integral of the top function minus the bottom function. But because it's an area, it's actually a definite integral. How do I find these two values here? Well, those two values refer to the endpoints of the shaded region. So it's going to be here, that will be my A. This point here, that will be my B. How do I find them? The limits obviously come from the endpoints. The endpoints come from where? How do I find them?
The y coordinates.
What do you mean subtract? What are those points called? What would you call them?
Oh, the critical points.
They're not critical points. Critical points where derivative is 0 or undefined. I have two functions here crossing each other here and here. What are those points called?
Intersection.
Intersection points. How do you find the intersections?
Equal to each other.
Set them equal to each other. Technically, you substitute one into the other, but you can think of it as setting them equal to each other, right? So I take y equals x squared, so I'm going to take x squared and plug it into the y over here. So therefore, I need to solve this equation, plus 2. How do I solve that? Say equal to 0, it's a quadratic. What do we get? Try to FOIL. Does it FOIL? X and x. What do we have? -2 plus 1. So I get my x is 2 or my x is minus 1. Which means that this number here is minus 1. That number there is 2. So the area I need, the area between those two functions, is going to be the integral from minus 1 up to 2 of what am I going to integrate? What's the expression I'm going to put here? X plus 2 minus x squared. Right? Remember, it's going to be the top minus the bottom. Right? And in this shaded region, the x plus 2 is the top, the x squared is the bottom. So I take the top minus the bottom. So in other words, I will have minus 1 to 2 of x plus 2 minus x squared dx. What would I get there? Antiderivative of x. X squared over 2. Antiderivative of 2. 2x. Antiderivative of this. X cubed over 3. I'm going to plug in minus 1 and 2. So I'll have 2 squared over 2 plus 4 plus 2 times 2 minus 2 cubed over 3 minus parentheses minus 1 squared over 2 plus 2 times minus 1 minus minus 1 cubed over 3. And I think I completed that. The answer would be 9 over 2. So make sure you try that and you get it. We'll do more examples next time, but if you want a shot at the bonus problem, I can give you the examples that I'll try next time. You can try them on your own. For this one, don't graph it. Think of another way that you can determine who is top and bottom. So remember, next class we have a test. We'll do these after the test because the test is only part of the class. And that's it. See you guys on Wednesday.